So thank you very much. Thank you very much for waking up and coming this morning. I'm a bit confused because I prepared very, very simple lectures, I mean, low level, in the spirit of the undergrad and grad lectures I gave in Bangalore 2 years ago. It's a bit redundant with that, by the way. And in the room here, there are only specialists. And I'm absolutely sure that about each part of the lecture, there is at least one person who knows things much better than me. And all of you know everything. So I'm sorry if I'm going to bore you. I mean, we are just very few. If you're bored or if you want me to go faster, just tell me. I mean, there's no. For example, of course, Urna knows much better than me the first part, today's lecture. I mean, there's no point. You can even go back and sleep, Urna, if you wish, or work on something else. So I divided my lectures in two parts. The first part will be about non-equilibrium physics, Galavoti-Cohen, Dzerzhinsky, all this framework. And tomorrow I will talk more precisely about exclusion process and a bit more the matrix ansatz and some results about current fluctuations and so on and so on. So the plan is here. I mean, it's a long plan. I'm not sure I'll be able to cover everything, but this is the aim. I mean, first of all, I will rush through equilibrium statistical physics, then talk about out of equilibrium and work identities, and tomorrow ASAP, exact results, open problems, and a little bit about MFT by the end, if I reach the end. Yes, that's the plan. And well, let's start. So just to put the framework back, I mean, if we start from statistical physics, even before we have to start with thermodynamics. And thermodynamics, of course, is the science of energy conversions, which means that you have to identify the different type of energies that are involved in your processes, and to be careful that these type of energies are not equivalent. And you know that when you convert one energy into another one, there is a kind of fee that you have to pay, which is quantified by this concept of entropy. Again, you're not going to learn anything from what I'm going to say. Maybe if you have to give lectures, maybe it will give you ideas, a way of presenting them to undergrads. Okay, so I like this quotation by Onsager. I always put it because Onsager was one of the greatest masters in our field, and himself recognized that thermodynamics is subtle, complicated. Although there is no high-brow mathematics involved, keeping the signs and the 1/2 and understanding what's going on is difficult. Okay, so energy, we know what it is. This is mechanical energy, potential energy, people leaping, but we know that it can be converted into heat, and this is the first principle. Okay. Energy is constant in the universe. But we also know that things are not always time reversible, that processes, if you make a picture, a movie, and you pass the movie backwards, things will seem odd. And the reason is that, in fact, it's related, in fact, and this is what Clausius discovered. Clausius, but before even Carnot, let's be a bit chauvinist today. So Carnot, this great French guy, discovered that all processes are not possible and cannot be realized in nature. Some mechanisms are possible, some are not. And one needs to have a well-defined criterion to separate allowed processes from impossible ones. So this is this groundbreaking work of Carnot, which was then put into a precise framework by Clausius, Kelvin, Planck, but also Einstein, in fact. Einstein was a major thermodynamicist. I mean, maybe it was even his, you can say, his basic first works were really thermodynamic works. And some people who have studied, maybe you know that also, who have studied this miraculous year of 1905 of Einstein, and the wonder was, how can a single person, even a genius, write 5 papers, one on electrodynamics of moving bodies, relativity, one on Brownian motion, weighing molecular weights, and one on photoelectric effect. I don't remember what was the precise title of this paper on photoelectric effect. And there was the other one on E equal to mc square and another one on Brownian motion the same year. How can a single guy work on so different fields? And in fact, some physicists and historians of physics have come to the conclusion that the common ground on of all these papers is indeed thermodynamic. I mean, Einstein had a thermodynamic approach on all these problems, and he really, I've not read the paper about the photoelectric effect, but people claim that it's a paper about thermodynamics. I mean, he really analyzed the photoelectric effect as a thermodynamicist. Of course, Brownian motion is closer to thermodynamic, and his reasoning that led to this Einstein relation is a purely thermodynamic reasoning. And even this is less clear, but relativity, his approach was really like a thermodynamicist, to try to construct a framework and something very general based on principles. So anyway, so before him there was Clausius and Kelvin Planck, which gave two ways of quantitative manners of expressing what we call the second principle, so which was first discovered by Carnot, analyzing machines, and the really quantitative ways to introduce this entropy. This was done by Clausius. So entropy is a word that was coined by Clausius. It did not exist before 1851. It appeared in his book, and he really coined it because he wanted to construct a word which sounds like energy, so on purpose, and he used, in fact, Greek roots to construct these words. And I don't know much about Greek, but I read that entropy contains this en, which means something inner, something intrinsic, in, and tropos, tropy, tropism, tropic of Cancer, tropic of Capricorn, which means a kind of motion, direction. So it's a kind of innerly motion that directs you towards something. Okay. So entropy, and he just coined the word. I mean, there was no concept like that before, and you can put the second principle in this very imprecise but nice way, saying that the entropy of the universe increases. Okay, and as we all know, a system has a tendency to minimize energy, increase entropy. So if we analyze a system which is in contact with a unique reservoir at temperature T, the good object to study is the free energy, which embodies these two things together, energy minus time, entropy times temperature, and a system at a given temperature in contact at a reservoir at a temperature T has a tendency to minimize its free energy. This is the good potential, the good thermodynamic potential to use in such framework. A nice theorem, again, which was known in the 19th century, is that free energy can be represented as, can be understood as a maximal work that you can extract from a system in contact at a reservoir, with a reservoir at temperature T. So we know that if you have a piston with a gas, a non-adiabatic piston, so heat can flow in and out, and we have an expansion of this piston from a volume VA to a volume VB, the maximal work that is available from the piston, the maximal work is at most the decrease of free energy of the system, of the gas and piston system. So in the case of mechanical problem, we would have that the work available is exactly equal to the decrease of potential energy. If you think about hydroelectric effects or just making a mass fall down. But here, because of entropy effects, many-body effects, and chaos and so on, I mean, disorder, it's at most this decrease of free energy that you can convert as useful work. And as you know, the reason why I insist on that is that Dzerzhinsky, somewhere 150 years after this good old maximal work theorem, said something more about it. This is one of the reasons that people are so much in awe in front of Dzerzhinsky's result, is that people thought that this would be What could you say more than that? Well, we all know that Dzerzhinsky said more than that about this inequality. And indeed, if you want to be a bit pedantic, we should put the average work, because in fact in thermodynamics, only average quantities are considered. There are no fluctuations at all in thermodynamics. There is no broadening of the probability distribution, only delta functions. It is statistical physics that brings fluctuations into the game. Thermodynamics only considers. So for thermodynamics, there is no question of putting an average here because things are equal to their average. So, no. But we know that we should put an average. If we take a small enough system and do this experiment thousands of times, there will be fluctuations, and we should put here the average work. Okay. Okay, I'm not going to give you the proof, you all know about it, but the proof of this inequality requires both principles, first one and second one. And by the way, the dissipated work divided by temperature represents the entropy generated by the process. So this maximal work inequality is nothing but, again, saying that during a process, the entropy of the universe increases. So it's absolutely perfectly equivalent to the second principle, but you have to use, of course, conservation of global energy to assess it. Okay, so it's statistical mechanics, BOLTZMANN and Maxwell, and other people, again, people like Planck, Einstein, and so on. These are the two founding fathers and mothers. And BOLTZMANN never wrote S equal to K log omega. Again, because you know all the subject, maybe some anecdotes you don't know, but probably you know them too. This way of writing things is again due to Einstein. As far as, I mean, either Planck or Einstein, but I think it's even Einstein who, he didn't use the same notations. I think there was a W here instead of an omega, but okay, BOLTZMANN knew about it, maybe wrote it in words, but it was never written like, you know, compact formula like that. But of course, it is due to BOLTZMANN and rightly attributed to BOLTZMANN. So this picture also is very familiar. This is a poor BOLTZMANN's grave in Vienna. I've never seen it. Maybe some of you have been there. And Mozart is also in the same graveyard. So it's, you know, very, very big people are sleeping there forever. And okay, so this is BOLTZMANN's face, BOLTZMANN's statue. And the connection between thermodynamics and statistical physics, which is made by Boltzmann's identity, Boltzmann equation, can also be made through the free energy. If you consider the canonical ensemble, then we know that the partition function that normalizes the canonical distribution in a system at a given temperature T, this partition function is nothing but the free energy in disguise. So if we are able to compute the partition function of a system, for example, the three-dimensional Ising model, then we know its free energy and we know its thermodynamic behavior. We know about its phases and many other properties, exponents and so on and so on. So at least in equilibrium statistical mechanics, we know where to start from. We have to normalize a distribution. And this distribution is made from the energy of microscopic configurations. So it can be in principle constructed as soon as you know the Hamiltonian. Of course, it's not easy to do, but we have a procedure. And because it's a distribution, it has some width, so there are fluctuations. Things are not equal to their averages. Statistical mechanics is stronger than classical thermodynamics because it predicts fluctuations. And the major fluctuation, if you have no average behavior, if everything is around zero, so the basic object that exhibits pure fluctuations, the purely fluctuating thing, is the Brownian motion, which was discovered by Brown in the middle of the 19th century. Brown, so there are a few nice anecdotes about Brown. Brown was a great friend of Darwin. He was a botanist, so he was using microscopes and so on. And he was not he was a non-trivial guy. He's the guy who discovered that cells, human cells, vegetal cells, and so on, have nuclei. So the nuclei which contains DNA. Of course, no idea of DNA at that time, but this major object inside not all eukaryotic cells, this nucleus, was discovered by this guy. So we as physicists know him as just a kind of adjective for Brownian motion, but he was a major biologist, botanist at this time, and Darwin nicknamed him the Prince of Botanists. So even Darwin had a huge admiration for this guy. And he never published his thing about Brownian motion. This circulated as a memoir. At this time, people were not obsessed about publications and age numbers and so on and so on. So he just wrote, kind of booklet, maybe even 2 booklets that went around. He was a Scottish guy. And in fact, it was not unnoticed at all. I mean, people talked about it. It was a kind of, this jittering motion of everything, because he tried it on many, many different things. For example, at the beginning, we all know that he tried on some pollen pieces of pollen, and he thought that this jittering motion is probably related to a kind of principle of life contained in this pollen. So motion means life. And then he realized that no, of course, you can put any inert material and it will exhibit the same jittering motion. And he went on to try different materials, and he even went on to try with a small piece of the Sphinx, this kind of big statue which is located in Cairo next to the pyramids, which is just a pure piece of stone. I mean, so this is again, I think, very colorful of this 19th century colonialist Britain, where people had access to different things and so on. So yeah, so he understood that this motion has nothing to do with life and is a kind of general, universal thing, but had no explanation. And this was a kind of puzzle. I mean, many smart people tried to develop a theory to understand what was happening here. Many people understood very early, by the end of 19th century, that this was somewhat contradictory to the second principle. It is not, but they felt that if you have motion, you can extract work from it. You cannot. I mean, this is Feynman's ratchet thing. But they thought that if you can harness this motion to a small motor or to a small device, mechanical device, you may extract work from it. But this motion is produced at uniform temperature. So this would contradict Carnot's principle. And people were just very much puzzled with that. And this was, in fact, one of the 2 problems that Poincaré selected as a major problem at the beginning of the 20th century. So the other one was electrodynamics of moving bodies, what we call now relativity. And himself was working on this relativity principle, but he had one of his very good students called Louis Bachelier to try to understand what was going here with this Brownian motion. And indeed, Bachelier, who became one of the first financial mathematicians, if you wish, developed a pre-theory of Brownian motion. So intelligent people like Poincaré and Einstein, of course, at the same time, understood that this was a major puzzle, this Brownian motion. Okay, so the theory was done by Einstein. We again all know that the important observable is not the motion, the speed of the Brownian particle, not really its position, but rather the quadratic average, the quadratic mean of the positions, which diffuses linearly with time. And we know that this coefficient d was computed by Einstein in 1905. Einstein gave a formula which relates the diffusion constant to temperature, viscosity of the liquid, size of the pollen grain, and the Avogadro number. And so this formula was found simultaneously by a guy, I forgot the name of this guy, in Australia. One of our, not Stokes is this 6 by Sutherland, yeah. Stokes is this formula. Sutherland, yeah. One of our colleagues, Bertrand Duplantier, is a big defender of the memory of Sutherland. And by the way, if you're interested not only on historical aspects, but also on calculations and relation with SLE and all these things, a kind of very wide coverage of Brownian motion from its very beginning up to SLE. And there has been Bertrand Duplantier wrote an absolutely beautiful piece of art, piece of work. He spent 1 year working on that, a kind of memoir again, which is in the archives, 100 pages long, which contains a lot of physics, a lot of anecdotes, a lot of references, and which goes really very far. Starts from nothing and goes through the whole story. So this formula is fantastic, again, because this is maybe not the very first, but maybe the first testable formula. There was another formula of the same kind by Maxwell about that related viscosity and Avogadro number, but this is the very first formula which relates quantities which are macroscopic or semi-macroscopic, d, r, t, eta, and a, with 1 over n being the Avogadro number, and 1 over n being the mass of the proton. So this is an incredible formula in which all quantities are at our scale, or the scale of an optical microscope, at least. So fraction of millimeters, things which were completely experimentally accessible 120 years ago, and 1 over n, which is 10 to the power minus 23, which is the mass of a proton. Nobody had an idea of what a proton is at that time. Mass of an hydrogen atom. So this was tested by Perrin just a year later. And Perrin had this nice sentence in French, but I translated it in English. When he did the experiments, he described them, so I'll just say it in French, j'ai pesé l'atome d'hydrogène. I weighted the hydrogen atom. Again, people, not all of them believed in atoms at that time, no electronic microscopes at that time, no way of seeing, no field microscopes, no way of seeing atoms, but with simple optical means. He used only optical microscopes. He used simple devices with this, pipette and small balls of gum, and he was able to weigh the hydrogen atom. This is something absolutely incredible. Okay, but the paper of Einstein contains much, much more. It contains this beautiful relation between diffusion constant of this Brownian particle at equilibrium and linear response. If you suppose that the Brownian particle, contains some charge and you drive it by an external field, it will acquire a limiting speed which will be proportional to linear order to the force you apply to it. The coefficient is a response coefficient, this sigma. It is a susceptibility, a conductivity, a mobility, call it whatever you like. And in this founding paper on Brownian motion, Einstein found that linear response coefficient is linearly related, is equal to, up to kt factor, to fluctuations at equilibrium. And this was the seed of all this formula, all this theory, we can say, developed in the 50s and 60s by notably the Japanese school, Kubo et al., but many other people. There are books about that, which is called linear response theory, and which somehow constructs what people used to call non-equilibrium thermodynamics, also this Belgium school, de Groot-Mazur, and all these people, but which aims to construct a thermodynamics which goes slightly beyond classical thermodynamics and which allows to compute transport coefficients. And up to now, this Einstein relation or its avatar, its more elaborate avatars, Green-Kubo formulae, they are the basic tool to compute response coefficients, susceptibilities, and so on in solid-state physics. The other basic tool is Onsager's reciprocity relations in 1931. So Onsager really introduced the concept of detailed balance and all these reaction diffusion processes. 2 very short papers written in a beautiful English, very, very pristine papers. And he understood also that if you consider linear response coefficients, that we can call LIK, so I just consider a crystal with no special symmetry on which you put in 3 directions, 3 different gradients, 3 different differences of temperatures, T1, T2, and T3. Currents will appear, heat currents will be developed due to this gradient of temperatures in the crystal. Because of anisotropies, you can very well apply a gradient of temperature in the horizontal direction and get a vertical current. Nothing forbids you from that. And there will be 9 response, 3 by 3 matrix, 9 response coefficients. But Onsager discovered that in fact there are only 6. The matrix which couples, LIK matrix, which couples the gradient of temperatures with the response currents, GIs, is symmetric. And it is symmetric for very profound reasons. It's symmetric because of time reversal invariance of physics, forgetting about beta decay, of basic physics, of Schrödinger equation and Hamilton equations. So it's symmetric for deep reasons. So this identity cannot be derived from the 2 or 3 principles of thermodynamics, from Carnot's principle, from Joule's principle, and from Nernst's principle. So it goes beyond classical thermodynamics. And this is, in fact, what Onsager got his Nobel Prize for. He didn't get it for helium. He didn't get it for Ising model that for us people, maybe it's the major achievement of Onsager, but he really got it for that. And this is indeed a major achievement, even bigger than the previous ones that I quoted, because if you consider physics, first of all, this gives you the basic quantitative theory for many effects, thermoelectric effects, Peltier, Seeberg, and so on, Joule, Kelvin, and so on. But also, in fact, this kind of relation is general. So Onsager, in fact, was able to predict that if you have some effect, I don't know, I would just say something completely stupid, or I don't know, if you apply pressure to something, some magnetic field develops. It should exist, piezomagnetic something. Then automatically, the opposite effect will exist. Even if you have not discovered it in the lab, if you apply a magnetic field, then there will be some pressure. So if you apply pressure, some magnetic field develops. Inversely, if you apply magnetic field, some pressure will come out. So he was able to predict a priori, and not only qualitatively, but quantitatively, the existence of a whole duality, in fact, in the world. And many effects, in fact, were discovered after that. Many of them. Okay, so these 2 things, Einstein relation, Kubo formula, linear response, plus Onsager reciprocity, they went together as this global non-equilibrium thermodynamics theory of the 60s, and they were the basic founding blocks of what we knew about non-equilibrium statistical physics up to the 90s. I mean, there were important works around that, of course, but they were really the founding blocks. And this is, of course, at equilibrium or close to equilibrium. And I recall you, I maybe did not insist enough on that, thermodynamic equilibrium is really characterized by the fact that the fluxes between a system and its environment, whether they are mass fluxes, charge, spin, energy, whatever you want, they vanish on average. So there are no currents going through your system at equilibrium. Okay, so this I will go very fast. I mean, I think we don't really need to talk about these things. Just a very nice picture of De Gennes. I mean, I think you all heard about him, but this is this is by the end of his life. You see, he didn't live so long, unfortunately. Of course, he ought to be alive nowadays, but it is a very, very nice picture. He was one of the very few physicists in France who became a superstar. I mean, I think, yeah, he was really a superstar. Okay, so let's talk about dynamics. So the framework I'm going to adopt, there are many possibilities, is the Markovian framework. So I will discover, many of our talks, for example, your talk yesterday, really described the evolution of a system as a Markovian system. So there will be a master equation, and we suppose the system has no memory. It has some discrete set of configurations, typically, and you can go from one configuration to another with a rate m. So the only thing to remember here is that I write things in the opposite way that mathematicians do. So to go from C to C prime, you have to read backwards, C to C prime. So MC prime C is the rate of going from C to C prime. Okay. Mathematicians use the opposite convention, but then they have to multiply matrices on the opposite side. So the governing equation for Markov processes is the master equation for the probability distribution at a given time t, and this is just a balance equation. The change of probability of being in C at time t is just the rate at which you enter this configuration from any C prime minus the rate at which you leave this configuration. And so you can represent this Markov process as a network amongst configurations, and arrows represent possible transitions, and they are weighed by, probably I made a mistake here. No, it's okay. They are weighed by the rates. And as again you all know, if we decide to call this negative term minus the total exit rate from a given configuration, we redefine it as a diagonal term with a minus term, then the master equation can be rewritten as a very compact matrix equation. So it's a linear equation. It's a kind of Schrödinger equation, but the Markov operator has absolutely no reason to be Hermitian, to be symmetric. The rates are numbers, they are real numbers, so it has no reason to be symmetric. In fact, the Markov equation, the Markov matrix M, will be symmetric up to a change of basis, will be symmetric if and only if the system is at equilibrium. There is an equivalence between the fact that the Markov matrix is symmetric, has a real spectrum, and the fact that the system obeys detailed balance. We are going to see that immediately. Okay, random walker. If we now consider continuous configuration variable x, in fact, the Langevin equation is a kind of continuous space-time limit of the Markov equation. And so this is a Langevin equation, and to be more precise, the continuous space-time limit is rather the Fokker-Planck equation, and the Fokker-Planck operator is a continuous limit, is a continuous version of a Markov operator. This is the same thing. Okay, so this we have to tie it, this is dynamics, but we have to match it with thermodynamics. So the matching procedure is just made by saying that we want that the kernel, that the steady state of this equation, or more generally of the Markov equation, we want this steady state to be the equilibrium system. If we describe systems at equilibrium, we want that the steady state measure is nothing but the BOLTZMANN-Gibbs canonical measure. So this is one way of matching thermodynamics with dynamics. So we just plug this BOLTZMANN-Gibbs measure and enforce the fact that it is the stationary solution of the Markov operator of the master equation, which means that this gives us a certain number of constraints on the Markov rates, on the MCC prime rates. This will give us n constraints if we have n different configurations. But the Markov matrix is n by n, so there are n square rates a priori. So this is just a very light constraint on the Markov operator. This constraint is called global balance. Okay. Just the matching with thermodynamics. If we do the same game on the level of the Fokker-Planck operator, we shall say that the Fokker-Planck operator has in its kernel the BOLTZMANN-Gibbs measure, which is in the continuous space, is given by exponential minus the total energy, sum of kinetic energy and potential energy divided by kT. Well, if you just put it and plug it into the Fokker-Planck operator, this will give you back Einstein relation. In fact, this is precisely, maybe in more modern words, what LANGEVIN did. This is Langevin's way of re-deriving Einstein relation between this relation between diffusion constant and linear response coefficient, or Einstein relation that express the diffusion constant as a function of temperature and viscosity. This is the way that Langevin used. Just plug into the Markov operator and get the drift, the linear drift of the square average. Okay, this is Langevin. And this is Langevin with Einstein. Like Langevin was a personal friend of Einstein. And you know that Einstein faced a lot of controversies in the beginning of his life and even in the continuous, I mean, even later on, especially during the Nazi period in Germany, but even in the 1910, so on, many people did not believe in relativity. But Langevin was a very smart guy, maybe too smart for his own good, didn't work enough. And he was one of the first guys in France to understand the importance of relativity, and especially this E equal to mc square equation. People claim, at least in France, but maybe it's not true, that he was not very far from deriving it. He didn't derive it the first, but he immediately understood its importance. And he even proposed that Einstein should become a refugee in France in the early 1930s, proposing him for a job in Collège de France. Fortunately, Einstein did not accept because, well, France soon was invaded and became a very unsafe place for many people. Okay, so let's forget about history and let's talk about something even more important than global balance. This is detailed balance. You can just rewrite master equation in this form and then just expressing local exchanges between two configurations C and C prime. So you can say that the rate of change of the probability of being in configuration C at time t is the sum of all local currents that couple configuration C with any other configuration C prime. So just local 2x2 exchanges. In the stationary state, of course, the sum of all these currents, pair currents, have to vanish. But there is a principle of local balance, which is much stronger than global balance, which tells you that not only the sum of all these currents in the stationary state has to vanish in the steady state, but they all have to vanish individually if you describe a system at thermodynamic equilibrium. So this is a major discovery of Onsager 31. Having discovered that, he was able to derive his reciprocity relation using some other ingredients. But this is one of the major ingredients he used to obtain his reciprocity relation. So this local balance, detailed balance relation tells you that at thermodynamic equilibrium, this relation among rates have to be satisfied. So global balance gives you n constraints. Local balance, detailed balance, in fact, fixes all these rates over 2. I mean, this gives you n squared over 2 constraints on the, or maybe n squared minus n over 2 constraints on the rates. So it's much, much, much more stringent, much more strong constraint.
There will be such a function.
So I'm going the back way. I'm saying that this thing reaches thermodynamic equilibrium. P equilibrium is Boltzmann weight exponential minus e over kt. And at thermodynamic equilibrium, the rates which are unknown have to satisfy this. Of course, now we are much more interested in the way you formulate it, which is to forget about thermodynamic equilibrium and try to see if such a function exists. Okay, so maybe your question, Anupam, was, suppose, I mean, this, it's true. So this is also an interesting thing. Maybe again, most of you know it, but if you don't, this is an interesting fact. Detail balance is expressed in terms of the rates and some function p equilibrium. Okay, but we can say, okay, but I'm not happy with that. I would like to express detail balance only in terms of the Markov rates, because this is something which comes out of the blue, which I don't know a priori. To know it, I would have to solve the steady-state equations. So suppose I give you a Markov system, and you don't want to solve the steady-state equations, you don't want to get to compute p equilibrium, and you want to test whether detail balance is satisfied at the level of the rates. So this is in fact doable, and the way to express it is that if you take any cycle, C1, C2, C3, Cn minus 1, and any cycle in the graph of your Markov process, the product clockwise and counterclockwise of all the rates, so M, so I'm going to use a different notation, C1 to C2, which would be C2, C1. If I wrote it the way I wrote it on the transparencies, C2, C3, and so on, Cn minus 1, Cn, C1. This has to be equal to the backward rates. So C1 to Cn, Cn minus 1, Cn minus 1 to Cn minus 2, C2 to C1. So if for any cycle in your system, this identity is satisfied, then detail balance is true. And then you can reconstruct the equilibrium measure just by using these rates. Okay. This was your question, maybe? Yeah. Yes, I will. Yes, exactly. I will tell you about that. Yes, of course.
And that's one way you define this entropy at the very end.
Yes, this will just come later. If I still have, yeah, I will rush a bit. But okay, this is a non-trivial thing. I mean, that if you have this kind of identities, you can prove detail balance. And in fact, it's quite non-trivial. You have to play with graphs and adjust them. It's quite elegant. And I just saw a nice proof. So it's a classical thing in mathematical books, a Norris book, for example, on Markov processes. But there's a nice proof in a Zia and Schnittmann paper that maybe you know. So there's one paper of review by Royce, Zia, and Beate Schmittmann. I'm sorry, I'm not completely sure about the number of T and N's, but you know these people. It's not like that. Schmidt. Okay. I'm confused because I know her in fact quite well. But okay, but there's a nice. They have written a huge number of papers, but there's a review papers, maybe 5 years ago, in which they very carefully go through this proof. And again, it's a non-trivial graph theoretic. You have to count trees and see how they connect and so on. It's very elegant. It's not.
Should be satisfied for every cycle.
Any cycle. Yeah, of course. Yeah, of course. Otherwise,
Not just for 1 minute.
no. That's why no, of course. So it's very nice. I mean, they did not invent it, but they present it in a very pedagogical way. It's 2-3 pages long, and I personally found it. I love it. I mean, if I had more time, I would have maybe done it. But okay, so this is local current. Again, this detail balance relation. If you just balance out, because you see it's very asymmetric. If you put square roots and transfer parts here, you can rewrite it this way. This is the same relation. And if you now look at this equation deep into the eyes, you see that it tells you that this matrix is symmetric. So indeed, there is a very nice relation between the fact of being Hermitian symmetric and satisfying detailed balance, which is nothing but satisfying time reversal. Okay? And because the spectrum of a symmetric matrix is made of real numbers, this tells you that there are no complex oscillations. When a system is at goes towards equilibrium, it relaxes without oscillating. The presence of oscillation is a signature of non-equilibrium, if you wish. Okay, now I go to what Sanjeev was referring to, is a proof and a physical interpretation of detailed balance. So again, this is a very elementary thing, but okay, if there's a single person who doesn't know about it, I think it's nice to learn. If you take a Markov process, there are two things you have to know about it. First of all, the probability of going from one configuration C to C prime is MC prime C dt in the convention we adopted. Okay? And then what is the probability of remaining in a configuration during a time tau? Well, the time interval tau, the probability of remaining into configuration C is the probability of not exiting from it, not going out. Okay? And remember, I told you that what is the probability of going out? Well, the probability of going out per unit time is m c towards c prime, sum over all c primes dt. So this is the probability of exiting. So 1 minus this is the probability of remaining into configuration C during time dt. But this, we changed its name and we decided to call it the diagonal term. So 1 plus mcc dt, it is the probability of remaining during time interval dt into configuration C. Now if we consider a long time interval tau, we just have to chop it into small pieces of length dt and multiply. This is Markovian, we have independence, there's no bad trick here. So we just multiply it and take the dt going to 0 limit, and this tells you this is nothing but, radioactive decay, what we learn when we are kids. It tells you that the probability of remaining in the configuration C during a finite time interval tau is exponential mcc tau. Don't forget that m is, the diagonal terms are negative here. Okay. By the way, I forgot to say, but because of this definition of the diagonal term, this ensures you that the Markov matrix is made of positive non-diagonal entries, negative diagonal entries, and the sum over all columns vanishes. This is continuous time Markov process. Okay, so we just need to know that. Configuration to jump, probability to remain. And now if we take a trajectory of a system and we just draw it in an abstract way, so we have a discrete, continuous time, discrete state Markov process. All this can be generalized to continuous states and so on. But suppose we have discrete states, so the system starts in C0, remains there up to time t1. At time t1, it decides to jump to C1, remains there up to time t2. At time t2, it decides to jump into C2, and so on and so on. Last jumps occurs at time tn, and final time is capital T. It is in Cn. We can very easily compute the probability of observing this trajectory. We start, suppose, at equilibrium or stationary state. This can be different in C0. Then we remain in C0 during time t1. During the short time interval dt1, we jump from C0 to C1. We remain in C1 during the duration t2 minus t1. We jump during dt2 from C1 to C2, and so on and so on. The blue things are remaining factors. The red things are jumping factors. So this is the probability of observing this trajectory. Okay? So Markov process allow you very simply to go from Markov process give you give you transition rates between configurations. You can very easily construct a measure on parts given a Markov process. Okay? This is nothing but a kind of path integral, what we are trying to do here. So now given a trajectory, there's a canonical trajectory associated to it, which is nothing but the time reversed trajectory. So what is a time reversed trajectory? It is just a function. This is a function, and this is a trajectory. C of t, the time reversed is C of capital T minus small t. So let's draw it. C of capital T minus small t starts at Cn, lives in Cn up to time capital T minus Tn, and so on and so on. I'm just drawing this back. Okay? So now this is another trajectory. We can compute its probability. Let's call it C hat, this trajectory. This is another bona fide trajectory that the system could adopt. Okay? The only thing is that now you start in the Cn configuration, so it has a probability to be observed. And of course, the natural thing, this is what Sanjeev was alluding to, is if we want to measure how much a system is time irreversible, or let's say the opposite way. A system will be time reversible if you can make a picture of it and pass the picture backwards and not being able to say that something strange has been done to your movie. Which means that a system is time reversible. This is a criterion if every trajectory has the same probability of being observed as a time reversed one. So of course the natural thing to measure time irreversibility is to take the ratio of the probability of observing C divided by the probability of observing C hat. Okay? If we take this ratio and you look at these two formulas, well, you will see that the blue things, the blue guys here, which just express the probabilities of remaining in a given configuration for a given duration, the blue things are the same. I mean, if I just reverse this trajectory, the length of these plateaus will be the same. And indeed, they are the same. So if I take the ratio, only the red guys remain together with the initial conditions. Okay? So the ratio between forward and backward probability of trajectories is just given by this very simple fraction. And now comes the miracle. So suppose we have detailed balance. And if I have detailed balance, maybe I should rewrite detailed balance. If you remember, detailed balance was written here. Detailed balance, you can just observe, interpret it as a kind of zipping thing. If I have this equation, I can move Px backwards and get to Pxc and switch C and C prime. Okay? So let's do this thing here. If I move Pxc0 through MC1 C0, I will get Pxc1 and MC C0 C1, this guy. I get here Pxc1 multiplied by M C2 C1. I can move it through. I will get M C1 C2 and Px C2, and so on and so on. So I just zip this thing through. This will give me all the red guys here in the right order, because all these arguments will switch, and I will get Pxcn, and in fact, this ratio will be equal to 1. So detailed balance implies time reversal, and the converse property is trivially true. If I have something which is time reversal invariant, I just apply it to a single step trajectory, and of course if I impose that this is equal to 1 and just do it for a single step trajectory, which means just taking Cn equal to C1, okay, then of course I get detailed balance. So detailed balance is equivalent to time reversal. So in fact, time reversal, detailed balance, thermodynamic equilibrium, all these things are now equivalent, but this is not trivial a priori. This is Onsager's discovery.
So it seems that we have to use this continuous time, because when you compute this,
yeah, this thing? Yes, but this is a proof for continuous time.
right,
But you could write a proof for no.
diagonal terms, they will always cancel.
Yes, exactly. Instead of having exponentials, you will have powers to the time, and
Because it's more,
because I'm used to play with the ASAP and with continuous time dynamics. But if you could do it with LANGEVIN, I mean, you just have to take a framework and adapt your proof to any framework you prefer. So you're right, I chose this one. But any dynamics which is time reversible, you will have an ad hoc proof. I'm not sure that there exists a kind of overarching proof for all possible dynamics. I think it is like Dzerzhinsky. You have to prove it for Hamiltonian dynamics, you have to prove it for Markov, you have to prove it for Noether, you have to prove it for Langevin. That's why you have so many papers. I don't think there's a kind of, meta proof which you can specialize. But it could be, I mean, maybe Raphael Chetrit has written a kind of meta proof that can be, spat out in all possible dynamics. But you're right. I mean, I like continuous time dynamics. Mathematicians prefer discrete times usually. Huh? Okay, now let's go out of equilibrium. I'm running out of time. So, okay, out of equilibrium. This is this picture. This is, this is. Maybe we should take it as a kind of logo of non-equilibrium. This one or any other one. Some people prefer to put squares here and so on. But okay, I mean, this picture, I don't know. I personally saw it in one of Bernard's lectures, but everybody uses it now. Two reservoirs at different temperatures or different chemical potential or different electrical potential that you connect by a small wire which is conducting. And now you wait long enough, but of course you wait long, but the reservoirs are very big, so they are not depleted. So their potentials are fixed, their temperature are fixed, and you reach a steady state current, and you want to describe the statistical mechanics of the system. The average current will be given by Ohm's law at linear order, or Poiseuille law, or Fick's law, or Fourier law. Again, depends on which precise context you're working on. But we want to understand more. We want to be able to understand this for microscopic dynamics, and we want to understand the fluctuations of these currents. We also know that if the temperature is low here, of course, if it's high here, well, if the temperature is high here and low here, the profile of temperature on average will be given just by a linear profile, kernel of the Laplacian, kernel of the heat equation. But we want to understand the fluctuations of this profile. Okay, there are so many things to understand that we are all trying to do. We want to understand what plays the role of entropy in this game, and so on and so on. Okay, so this is the fundamental non-equilibrium picture, and I try to sell you, well, I think I don't need to sell here. Everybody in one disguise or another has worked on the exclusion process, but a kind of microscopic model that mimics this general picture is the AZEP, where particles, we shall talk about it more tomorrow, where particles hop from left to right and right to left with different rates, and which are connected with two reservoirs. And this model is, okay, very simple, it's a kind of caricature, but still it has been the subject of thousands of papers and has now become even a part of combinatorics, mathematics, very highbrow developments that Tomohiro is going to tell you about. Okay, another. Yeah, to be the same one. Yes, it's a proof. So in fact, the proof of Zia and Schmidtmann goes further. They in fact just get this as a byproduct. They in fact prove a very nice formula due to Kirchhoff, I think. Kirchhoff formula. Again, I don't know how many C's and how many F, and the same Kirchhoff as electrical networks, which was in fact a very deep graph theorist. And Kirchhoff formula allows to express, so this is the main part of their proof, allows to express the stationary probability in terms of the rates. So it's a very general formula. Forget, of course, in the case of detailed balance, the formula becomes very simple. But in general case, there is a formula, a tree-theoretic formula, which allows you to compute, well, not to compute because it's not handy, but which allows you to express the stationary state in terms of the rates of the Markov process. Very beautiful formula. So this is what they do. And then they spell it out in the simple case were cycles. Because in fact this formula uses cycles, uses ratio of cycles like that. Of course, when the ratios are equal to 1, the formula just simplifies immensely, and then you get a very nice formula. So, but another nice context in which non-equilibrium appears is life, molecular motors proceeding along the cytoskeletal fibers. And this is important, and many people who work in soft condensed matter claim that because our cells are at 37 degrees, 98 Fahrenheit, there is no Carnot motor possible there. There is no two reservoirs at different temperature. We are at very stable temperature, hopefully. But still you have things which are moving in cells and bringing things from one part of the cell to the other. So there are microscopic motors. And maybe the hope of some of the people working in this field is that studying precisely molecular motors instead of engine motors, instead of car motors, will lead them to some principles which are valid even for small number of small n thermodynamics, n being the number of degrees of freedom, and non-equilibrium, because here there's a huge exchange, of course, within cells. They are far from equilibrium. They are at stable temperature, but far from equilibrium. Well, Udo gave us a lecture last week, which was perfectly, in the spirit. He even said that we are at stable temperature, so temperature is well defined, though it's a non-equilibrium system. Okay, so now I want to talk about large deviations. I'm of course far from schedule. When we study statistical mechanics, we learn of two basic facts in probability theory. The law of large number. If I have a sum of binary variables that can be equal to plus or minus 1 with probability p and q respectively, we know that the sum divided by the total number of sample n converges almost surely to p minus q. If I throw a coin with probability 1/2, it can be tail or head. If I throw it 1,000,000 times, and I just count how many heads I have and divide by 1,000,000, this will go to 1/2. And the bigger the number of samples, the more accurate is this 1/2. And we know that fluctuations around 1/2 take the shape of a Gaussian, usually, if we don't go into Tracy-Widom things, which are correlated and more refined things. But at least the basic Laplace central limit theorem tells us that under very general hypothesis, independence is the simplest one, we have a Gaussian behavior with a width of the order of square root of n. Okay? But now we can ask a more refined question. We can ask a large deviation type of question. We can ask ourselves, what is the probability that we do 1,000,000 experiments with head and tails with a fair coin, and we observe 100,000 fair heads and 900,000 tails. This is unlikely, but this is possible. So what is the probability that we observe a ratio positive outcomes divided by total number of experiments equal to R, where R is not the typical, the nominal value P minus Q. Okay? P being the probability of having +1, Q being the probability of having -1. So if this R is not the nominal value P minus Q, this probability when n goes to infinity will take an exponential form. This is known as the large deviation principle, and there will be an exponent which quantifies the rate of convergence toward this large number theorem, and this function phi of R, which of course vanishes when R is equal to this nominal value, because we know that this probability is of order 1 for 1/2, 1/2. So this function phi of R is the rate function, but we also call it the large deviation function. Okay, for this problem it's very easy to compute it using Stirling formula, but this is a slightly less trivial exercise if we take an asymmetric random walker alone on the infinite line. We know that the position x of t at time t will be x of t will be of the order of p minus q times t, p being right jumps rate, q being the left-hand jump rate, but we can ask ourselves what is the probability that the empirical speed measured after time t is equal to v, v being different from p minus q. So this takes a large deviation form. Now time plays the role of the large parameter, and a nice exercise to be given to undergrad students is to compute this g of v. Okay, so it's not so trivial. I mean, you see, it's not a simple, it's not horribly complicated, but it's not a very simple function. It requires some, I mean, already it requires something. Okay, but this is a positive function that vanishes at p minus q. It is a convex function, so it has the shape of a, potential, typically. And it has a nice property that g of v minus g of minus v is simply linear in v. So here it's just a remark, but for the people who knows it, which means probably everybody here, this is a kind of very simple occurrence of the Galavoti-Cohen identity. But here you can just check it. Okay, so another way of saying it, because remember that g of v is the log of the probability. So if we compute the probability of observing an empirical speed v divided by the probability of observing an empirical speed minus v, and now we spell out the definition that this is exponential minus t g of v, this is exponential minus t g of minus v, and we have this identity between g of v and g of minus v, we see that the ratio of these two probabilities in the long time limit, I should put limit when t goes to infinity and so on, it's equal to a pure time exponential times a function which is just a linear function. So you can see this ratio again as a kind of analogous of the ratio between a trajectory and the time reversed trajectory that we talked about just before. So this is again another occurrence of the Galavoti-Cohen theorem in this very simple context. I would like to prove it, but I'm running out of time. Maybe tomorrow then. Okay, so let's call about fluctuations. If we consider now classical thermodynamics and statistical mechanics, we take a big box of volume V and temperature T with n particles, and we take a smaller box, let's say a box of 1 liter in this big room. We know that in the smaller box, there will be nominally the number of particles in the small box, small n, but it will be nothing but rho 0 times the volume of this small box, small v. So rho 0 times v is a typical number of particles here. Rho 0 is the ratio capital N divided by capital V. But we can ask a large deviation question. What is the probability that the empirical measured density in the small box is rho, which is a priori different from rho 0. We make an experiment here, we count the number of particles in this small box, and we get something which a priori could be 10% more or twice as big. It's unlikely, but who knows, than rho 0. So what is this probability of observing an empirical density rho in the small box? Again, it takes a large deviation form with a rate function capital phi of rho. And this rate function, this is a miracle. You can compute it from equilibrium statistical mechanics. This rate function has to vanish at rho 0. Well, this rate function, if you compute it using statistical physics, I will just outline the proof here. So it is just the ratio of the partition function for this small volume times the partition function for the rest of the volume divided by the partition function of the total volume. And now if you just plug in the relation between partition function and free energy, you will get that this rate function is essentially the free energy per unit volume in your system. So there is a strong relation at equilibrium between large deviation functions and thermodynamic potentials. You can reconstruct thermodynamic potentials up to some constant and some linear factor. Okay, you can reconstruct the thermodynamic free energy in terms, you can re-express it as a large deviation quantity. So if you knew nothing about thermodynamics, statistical mechanics, but you're an expert in large deviation theory, you can reconstruct classical thermodynamics using large deviation theory. This was done in the 70s by Ellis, okay, re-expressing. And again, we all know that there's a very nice review paper by Hugo Touchet who does that. This has become a classic paper on large deviation. I think it's a physics report. So he introduces large deviations, Donsker-Varadan, and so on and so on. And in one of the chapters of his review, he does this work precisely to reconstruct StatMech using large deviation. But this was done before by Ellis. By the way, Touchet is a student of Ellis, so there's affiliation, of course. Okay, now suppose that instead of taking only one box, we take plenty of boxes. So now we are not only interested in the empirical density in one box, but we just pave the whole room by 1 liter small boxes, and we want to have an empirical density rho 1 in the first box, rho 2 in the second box, and so on, up to rho k in the last box. So in fact what we are, yes?
But Galotti kind of symmetry is only for current fluctuation.
No, it's much more general. We'll come to it.
Even for deviation for this kind of.
So it's a kind of, it's not completely general, I mean, it's not for anything. But if you have some properties, the large deviation function of this property satisfies an identity. I'm going to prove it if Abhishek rushes and stops the countdown. I'm joking. Or maybe tomorrow, I mean, okay. It's coming, okay, but I'm talking too much. So now suppose that instead of taking one box, we take plenty of small boxes and pave the whole room, the whole large box, by small boxes. So we want to have the probability of having rho 1 in the first box, rho 2 in the second box, rho k in the kth box. But this is nothing but telling you what is the density profile. Because if we take very small boxes, we know the density rho of x almost everywhere. We're just discretizing space. A similar calculation will tell you that, again, there will be a large deviation principle, but now f, this large deviation function, is a function of k entries. And if we do the same calculation, we'll find that the probability of observing rho 1, rho 2, rho k is just this simple difference of free energies. And now if we take a continuous number of boxes, we'll have a large deviation functional, which is given by that. Is it clear to everybody?
So that's one constraint that
Yes. So no, it's taken into account in this difference, in fact.
No, like yeah.
In fact, this is because I have this is the reason I have the free energy and not the Gibbs, the other potential, you know, which allows fluctuations of the number. So here I do take into account the fact that the last one, in fact, this comes here. If you do the calculation precisely, sum of nk's has to be equal to n, and this comes here. So you see, now you have a free energy, you have a large deviation functional, okay, because we are interested in what is the probability of seeing a density profile which is a non-uniform density profile. So it's a functional large deviation function, and this functional large deviation function is nothing but the integral over the volume of the difference of the free energy evaluated at this non-typical profile minus the free energy evaluated on the typical flat profile.
It is basically, again, exponential minus beta x trace over all configurations, but with the given rho profile. It's like z, the partition function.
Yes.
So if I want to construct it from a given Hamiltonian, so I just
Okay.
do it to the minus beta h, but then it's a trace over all configurations with a given profile.
Yes, yes, but here I don't even, yes, you're right. But here it's really given like that. Profile is just number of particles in a given box.
But this I'm doing for each box. But
Yes.
if I just wanted I was given a total Hamiltonian of the system.
Yes.
Then I would just do, if it's with a lot of interactions and all.
Okay, yes, then I
Then
would
I
have
just do
to,
that.
yes. Here I consider that interactions are small, so I can break it. It's a product measure. But otherwise I would have to trace out over this profile. This is what is done for ZEP, for example. Yeah. We know the microscopic measure, and Derrida, Leibowitz, and Speer have traced out over this given profile. Okay, so you see there is a very nice relation between free energy functional and, 2 seconds, free energy and large deviation functional. Can I take 2-3 more minutes? Yeah. I will stop at a kind of logical place. But now we can ask the same question in the non-equilibrium framework. We can put two reservoirs at different temperatures. There's a current going from left to right. This average current is given by Ohm's law, if you want. Difference of potential divided by resistance, or any avatar of the Ohm's law. But we can ask ourselves, what is the probability that the total charge transported during time t divided by t, so the empirical current, is given by something different, half, or twice, or 10% more than the current predicted by Ohm's law. Again, this will take a large deviation form, and we want to characterize the fluctuations of the non-equilibrium state by computing this large deviation functional. So at equilibrium, large deviation functions are thermodynamic potentials, but you see they can be very well defined far from equilibrium. Nobody prevents us from doing it. And the rationale which has been developed by many people in the last 10-15 years, I mean, there are so many names, Galavotti, Cohen, Jarzynski, Lebowitz, Christian Maes, Derrida, Gianni, I mean all the people we show here, Herbert and so on, is that these large deviation functions play a role akin to that of non-equilibrium thermodynamic potentials. Okay. So maybe this I will skip. Well, going fast, but often what we can compute are generating functions in probability, and large deviation functions are given by Legendre transforms of these generating functions. So okay, I will close now. Another question we can ask is that we know that on average we have a linear profile, okay? Whether it is a density profile, energy profile, temperature profile, but we can ask what is the probability of seeing a bizarre profile, this red curved profile. So we want to compute the large deviation functional of any given profile. Okay. Again, a question that one can ask out of equilibrium. Of course, it would be very, very nice to compute the joint probability of seeing a non-typical current and a non-typical profile. This would also take a large deviation form, okay, of this type. And then we would have a large deviation functional which depends on two profiles, current profile and density profile, two functions. And one big progress that was done by Jonah Lasigno's group is for so-called driven diffusive systems to give a general principle, an overarching principle that allows one to compute, in principle, to calculate this functional. Okay, so maybe I will stop here. So tomorrow I will probably reshuffle my lectures because I'm going slower than what I thought about. I will prove this Galavotti-Cohen identity using a similar reasoning that Onsager used for proving detailed balance. And then we shall go over, these things, and then we shall go into more specific results on the exclusion process. Okay, sorry for going a bit over, but I will stop now here. Yes, Arvind? Yes. So in fact, it is L times T which appears here. L, the size of the system, and the time. I don't know, as maybe some of you here know why it should be like that. I know that it comes easily out of the scaling. I mean, just by looking at, I mean, it is not, no, there is no global reason. It is really related to the diffusive scaling here. So, I mean, once you do this diffusive scaling, it comes out. If you have systems which do not obey, which are ballistic, for example, or do not obey diffusive scaling, I think Abhishek has studied with different scalings, I mean, in the case of current conduction in one dimension, then you may have other exponents, other scalings. But I mean, this is also related to this Fredlin-Wenzel theory. Somehow, this theory comes with a noise, which has a small factor in front of it. So this is a kind of WKB first order expression. And the small factor that comes in front of the noise scales inversely with time or size. But the precise powers that come out depend on the dynamics that you are looking at.
Yeah, this in equilibrium, that large deviation function is related to the free energy, like which is easy to see for the density example you have given.
Yes.
Right? But I can again ask for the current fluctuation in equilibrium, which is the average current is 0, but I can just, right? So what is the corresponding large deviation function now in terms of, I mean, what is the corresponding free?
So it's the potential mu, it's this chemical potential which will play this role, I think.
I mean, it should be related again some free energy, right?
So it's related to, because now you allow particles to enter and to go out.
Yeah.
So it's not free energy, it's, in France we call it Gibbs free energy, G.
Okay, so it will
this mu, I mean, G equal to mu n, chemical potential. So this is a thing that will appear if you allow exchange of particles. You see, here we allow exchange of temperature, so we get free energy. If we allow exchange of volume, we will get H, U plus PV. Again, I don't know the name of this guy. Helmholtz free energy. If we exchange the particles, we'll get chemical potential.
So even like for only for temperature, let's say I just look at the energy current.
Yes.
But at equilibrium, both the baths are same. So it will be given in terms of the same free energy?
Oh, the free energy.
It's just this, okay.
As far as I know, I think. What's your opinion?
No, suppose but suppose I want to...
Yes, but we can, for example, take the exclusion process, ZEP, with equilibrated reservoirs.
Yeah.
And there's a large deviation of the current here.
So the large deviation function for the current will have minimum at current equal to 0.
Yes, of course.
Yeah, exactly.